there is a city where roads do not exist, where water itself is the only path forward. No solid foundation stretches beneath it, no bedrock waiting just below the surface. And yet, against every rule of construction, this city has stood on water for more than 1,500 years. How is that possible? How does a city built almost entirely on sinking ground manage to survive for a millennium and a half, carrying the weight of palaces, churches, bridges, and centuries of human life? The story begins not with stone or grandeur, but with an empty, sinking lagoon. Long ago, people arrived here seeking safety rather than beauty. They were not looking for the perfect building site, they were running from danger, and this strange, waterlogged stretch of land was simply where they could hide. There was barely any solid ground to speak of, only soft, saturated soil and shallow water that shifted with the tides. Any ordinary structure built here would have sunk within years, if not months. So the people who settled this lagoon did something remarkable. They didn't fight the water. They didn't try to drain it or force the land to behave like solid earth. Instead, their engineers devised an entirely different approach, one that worked with the ground rather than against it. Beneath the surface, hidden from every eye, they built a secret structural system. That invisible foundation would become Venice's greatest engineering achievement, and it remains, to this day, the reason the city still stands. In this script, we'll walk through the full story of how Venice was built, from the very first pilings driven into the mud to the modern flood barriers protecting it today. It's a story of patience, risk, and extraordinary problem-solving. And by the end, you'll understand exactly how a city with no roads and no solid ground became one of the most enduring urban achievements in human history. The first challenge Venice's builders faced was the ground itself. Beneath the lagoon lay soft layers of mud, fine sand, and decomposed organic material, the kind of soil that offers almost no resistance to weight. Placing a heavy structure directly onto this surface would have been like building a house on a sponge. It would only be a matter of time before the entire thing slowly disappeared beneath the surface. Recognizing this, the earliest builders began preparing the ground methodically, one section at a time. But their real innovation came with the next step, driving wooden piles, sometimes by the thousands, deep into the sediment beneath a single structure. These piles were not driven down to reach solid bedrock, as modern foundations often are. Instead, they were packed so closely together that they compressed and reinforced the soft soil around them, transforming loose sediment into a dense, load-bearing mass. Each pile was cut to a precise, uniform height, ensuring that whatever was built above would remain perfectly level despite the irregular ground beneath it. This process was slow and unforgiving. Workers spent entire days, sometimes entire nights, standing in cold, waist-deep water, driving pile after pile into position. There was no shortcut. Every single pile mattered, because the strength of the entire structure above depended on the consistency of the foundation below. Alongside the piling work, controlling the water itself became essential. Temporary wooden barriers, known as cofferdams, were installed around construction sites to keep the working area dry long enough for the foundation to take shape. This was dangerous work. At any moment, water could break through these barriers and flood the site, undoing weeks of labor in minutes. Yet the builders pressed on, driven by the understanding that every pile they placed was becoming a permanent part of something far larger than themselves. This relentless battle against soft ground didn't happen just once. It repeated itself with every new building, every expansion, every generation of construction across centuries. Venice, in a very real sense, was rebuilt from the ground up again and again. Not because the city failed, but because that was simply what it took to build on water. Once the piles were in place, the next step was to create a platform capable of distributing the weight of the structure evenly across this artificial foundation. This is where Venice's hidden engineering system truly began to take shape. A structure that no visitor to the city would ever see, yet one that made everything above it possible. On top of the driven piles, workers laid horizontal wooden beams and planks, forming a solid timber platform. This layer was arguably the most critical part of the entire construction process, acting as the crucial link between the buried piles and the visible building above. Get this layer wrong, and no amount of skilled masonry above could save the structure from eventual failure. Above this timber platform, thick layers of stone and masonry were carefully placed, creating a stable base capable of bearing significant weight. Layer by layer, a complete system emerged. Soil at the bottom, followed by piles, then timber platforms, then stone, and finally the building itself, rising toward the sky. This layered sequence became Venice's defining formula, a repeatable method that allowed even massive, heavy buildings to stand securely on ground that, by all conventional logic, should never have supported them. Only once this hidden foundation was fully complete could construction of the visible building begin. And even then, choices about materials mattered enormously. Most structures throughout Venice were built primarily from brick rather than solid stone, simply because brick was significantly lighter, an important consideration when every additional ounce of weight had to be supported by that same underground system of piles and platforms. Stone was reserved for areas where durability against water exposure was essential, particularly in foundations and sections of buildings that made direct contact with the canals. One material in particular became indispensable: Istrian stone, quarried from across the Adriatic Sea. This dense, non-porous stone could withstand centuries of contact with water without deteriorating, making it perfect for the waterline sections of Venice's buildings. As construction techniques advanced and buildings grew taller and heavier, the need for precise load distribution became even more critical. Every wall, every column, every structural element had to align exactly with the timber and masonry system hidden beneath the surface. A misaligned wall wasn't just a cosmetic problem. It risked concentrating weight unevenly and destabilizing the entire structure over time. But Venice was never meant to be a single building, or even a single island. Over the centuries, it grew and spread across an entire archipelago. According to UNESCO, the historic city is composed of 118 small islands, all interconnected by a dense network of canals. Each island presented its own unique construction challenges, yet all of them were bound together by the same solution: water. While most cities are organized around roads, Venice took the opposite approach entirely, transforming water itself into its primary transportation system. The Grand Canal became the city's central artery, its largest and most important waterway, while a web of smaller canals connected the surrounding districts, threading through neighborhoods and linking every corner of the city together. Boats became the true lifeline of Venice. Nearly everything — food, construction materials, furniture, daily supplies — moved through the city by boat rather than by cart or wagon. This reality shaped the very architecture of Venetian buildings. Many structures were specifically designed with doors and entrances opening directly onto the canals, allowing goods to be unloaded straight from boats into homes, shops, and warehouses. Yet, connecting so many separate islands through water alone created an obvious problem. How could people move on foot between different parts of the city? The answer was bridges, and their construction relied on the very same engineering principles used throughout Venice: timber piles driven into the lagoon bed, topped with platforms, and finished with masonry above. These bridges were never simply functional crossings. They became the connective tissue of the entire city, transforming a scattered collection of independent islands into a single, unified, living urban landscape. Slowly, gradually, through centuries of bridge building, Venice stopped being a cluster of settlements and became one continuous city, Among all of Venice's bridges, none achieved more fame than the Rialto Bridge. Its foundation followed the same time-tested method used throughout the city, hundreds of wooden piles supporting the stone structure above. When construction began in the 16th century, workers spent months driving these piles deep into the lagoon floor, ensuring the finished stone bridge could bear the weight of the thousands of people who would cross it daily for centuries to come. As Venice rose to prominence as a major maritime and trading power, the pace of construction accelerated dramatically. Palaces grew larger and more ornate. Churches became increasingly elaborate, reflecting the city's growing wealth and ambition. Warehouses, government buildings, and defensive fortifications began occupying more and more of the available space across the islands. Yet, with every new structure, the same fundamental question resurfaced. How can something this heavy possibly stand on ground this soft? And the answer, remarkably, remained consistent throughout Venice's history. Careful engineering, precise load distribution, and constant, ongoing maintenance. There was no single trick, no one-time solution. Venice's survival depended on discipline applied over and over again, building after building, generation after generation. Venice was never simply constructing buildings. It was constructing an entire trading empire on top of water, a feat of ambition matched only by the ingenuity required to make it physically possible. Every new bridge, every new palace, added not just to the city's beauty but to its structural resilience, reinforcing a network of engineering that operated silently, invisibly, beneath the surface of daily life. Of course, building structures alone was never enough to guarantee Venice's survival. The lagoon's water was in constant motion, and that motion posed a continuous threat to the city's edges. Waves, tides, and shifting currents gradually eroded exposed land and weakened masonry over time. In response, Venice developed an extensive system of embankments, seawalls, and retaining structures designed to protect its buildings, while also regulating how boats navigated through the city's waterways. Even with these protective measures, Venice was never entirely stable. The ground beneath the city continued its slow, inevitable process of consolidation and sinking, even as global sea levels gradually rose. Together, these two forces combined to create one of Venice's most persistent modern challenges: recurring flooding, known locally as acqua alta, a phenomenon in which unusually high tides push seawater into the city's lowest-lying areas. In 1966, this ongoing threat became a global crisis. A catastrophic flood struck Venice, causing devastating damage to historic buildings and irreplaceable works of art throughout the city. The disaster drew international attention and sparked a wave of preservation efforts aimed at protecting Venice for future generations. It became clear that historical maintenance techniques alone would no longer be sufficient. A large-scale, modern engineering solution was urgently needed. That solution eventually became known as MOSE. Rather than constructing a single permanent wall, which would have disrupted the natural flow of the lagoon and its ecosystem, engineers designed a movable barrier system instead. Massive underwater gates were installed at the three entrances connecting the lagoon to the Adriatic Sea. On ordinary days, these gates remained submerged, resting on the seafloor and allowing boats to pass freely in and out of the lagoon as they always have. But when forecasts indicate an especially high tide is approaching, compressed air is pumped into the gates, causing them to rise up out of the water. As they rise, the gates form a temporary barrier that separates the lagoon from the open sea, shielding the city from the worst of the incoming flood. Yet, even with modern flood defenses in place, protecting Venice from rising water is only part of the ongoing challenge. The historic buildings themselves require constant, careful attention. Even the wooden piles that have supported the city for centuries cannot be assumed to remain permanently strong. Research has revealed that some of these ancient foundation timbers have experienced biological degradation over time. a reminder that Venice's survival is never truly finished. It requires continuous monitoring, preservation, and care. Venice was never created by simply filling in a stretch of sea with soil and calling it land. It was the product of a centuries-long engineering journey, built layer upon layer through patience and precision. It began with scattered lagoon islands and evolved through timber piles, foundation platforms, and layers of carefully placed stone masonry. From there came brick buildings, intricate canals, connecting bridges, magnificent palaces, and finally, modern flood defenses designed to protect everything that came before. What we see today when we look at Venice, the palaces reflected in canal water, the bridges crowded with visitors, the narrow, winding streets, is only the surface layer of an extraordinary achievement. Beneath it lies an enormous, largely invisible engineering system that has quietly supported the city for over a millennium. Between the buildings run carefully engineered canals. Above those canals stand bridges built through the same painstaking process. And surrounding the entire city is the same restless lagoon that has challenged it since the very beginning. Venice never truly defeated the water surrounding it. That was never really the goal. Instead, Venice learned how to live alongside it, how to adapt its architecture, its infrastructure, and its very way of life around the presence of water rather than in opposition to it. And in many ways, that ongoing relationship, imperfect, demanding, and constantly evolving, remains Venice's single greatest engineering achievement.